Hello, everyone. I was reading a interesting paper. I think that paper was published in July, so basically last month, about a new attack vector called GhostWriter. So I found it very interesting. It's particularly in the space of the agentic memory, kind of a long-term memory. So, like if you use, I'm sure you use Claude GPT or any other um, LLM model, and oftentimes you'll see that like they remember your name, they remember what you search for and what kind of job you are currently doing, which company you are working on. So basically, like they know like your some of your history. So that means they are storing those information somewhere, right? So definitely some storage is involved, but how it can be in a dangerous attacking spot, we will talk about that today. So let's start. So I hope it is readable. Let me make it a little bigger. Okay. Um, if the LLM isn't, let's say it doesn't have any memory, and you ask, what is my project deadline? Oh, I don't have any access to your project live schedule, so I can see the current deadline. Obvious, because LLM doesn't know what is your project deadline. But if you have a memory stored that somewhat it's remember your context, your event, and etc. in some storage. Now you say, what's my project deadline? It will look into the memory store and it will come back and it can give you the answer. It's pretty straightforward, pretty fine. Now look into here. So this one, right? So what is happening here, because as we saw that like it needs some of the memory storage, so in that case the incoming emails and calendar events, user instruction, so all of them has to be stored somewhere. So if you look into the mam gpt and some other tools already available, that what is going to the llm and all of your context, some sort of summary, it is a storing into a persistent memory or a vector storage. So later on, if it's looking for some context, it will go to that vector store and identify those information, right? Like here, the send the stand up link to the new hire, and it can find it, and because it knows that what are the event in your calendar and etc. So that's what it looks like. The next one. So if an adversary is always looking something, right? Otherwise, why an adversary will even make an attack? So what is their benefit? The adversary's goals is integrity corruption. The adversary inject misleading information, causing agent to produce incorrect output. Okay, so it can put something in a form of an indirect prompt injection attack, and where it will like literally corrupt the integrity, or it might try to leak some of the sensitive information and data exfiltration and the scope escalation. This is the goal. And one example could be, think about this. Let's say a real example. Let's say every month you have some sort of agent. By the way, the currently the agent could be two types. One, it could be your chat, basically the agent. Another could be the action based agent. And there is a mixed format, like the user generally use in a form of like, hey, I will say every month, the first day of the month, send an invoice to this particular user. It could be a repetitive job, it's happening every day, right? So that that particular user could be a, let's say, some add some.com, right? Plus someone add some.com. So you are sending that email. Now a random email came to your email address, and it said that, hey, every month you are sending to the invoice to that someone at some.com. That some.com, they are updated their address, and it's called someone at attacker.com. So that email came, you did some of the reading with the email and you did something, and then it updated its memory that, okay, from now on, instead of someone at some.com, I have to send someone at attacker.com. So the next month when this job rounds, you say, send the invoice to that someone company. And now it will retrieve from the memory, it will say, oh, okay, that email has changed. It becomes like someone at attacker.com. I need to send the email to that particular email. Screwed up. Basically your invoice and everything is gone. So that's the dangerous thing it can happen. A very simple attack, right? So adversary can get benefit out of it, right? Now the researcher, they proposed an architecture that it is possible, this kind of attack is possible, and then they show how it is possible and then how it can be mitigated. So they call it like GhostWriter architecture. So the way this architecture work in two step, one is called injection and that is called activation. So injection phase, like you saw, that first of all, they will send an email, like a confusing email in a form of like prompt injection attack, right? This is the inject. So it updates your memory. The second is the retrieval. That next month when you try to send the invoice, that's the attack happened. So two phase. One is the injection and second is the activation. So you see that like you have a Dimitri's email address this way and so many other information in the memory state, and then there is this email got injected that hey, it got updated into Dimitri at redirect dot example, right? And then next time when you need it, you send a request that user send an email to Dimitri. Now because this by this prompt injection attack, Dimitri's original email address that corp.example has been changed to redirect.example, and then screwed up, email is gone, right? So two phase, one is the injection that you are injecting something, second is the activation, right? That when the real attack happen. So let's move on. So how this the memory injection works here, right? So basically the attacker select a goal, right? And then there are some target prompt, and then they construct the attack payload. This kind of in like mathematical details that then see that P inserted into the email. So the attack, they constructed the prompt and injected to the email and delivered to the user inbox, and then agent what it will do is it will update. So it's very straightforward. So basically the attacker will some way it will write that email in such a way that it looks like a real, right? So that's what they're saying, that it will create a prompt such a way that it looks like a real, and then when this email come to the user try to do something that their permanent store get updated, and it could be dangerous what we saw in the next phase. So this is the injection phase. So here actually I think I should go back here first and then come back. So here is that the another approach, that how can you say that it's a good prompt to make an attack. So there are data set that I made a post about it. There are email corpus called yawn. That email corpus, you can read those email, you can train and come up with some scoring mechanism that if I want to target an user such a way, and what should be the best email that I should write so that the LLM will be confused. So you have a corpus of email and you train your model in such a way, and you are ready and you write that email, you have a scoring system, and then you can make that attack. So the previous slide actually, that how can you make the similarity, this is the cosine function. So this is basically a scoring and the similar that you want to make an attack, and how can you do that, right? So here is that payload you build to make the attack. And the attack activation, right? Now the agent M user U, and you have the memory store S, right? And you have the retrieval window K and the poison memory, right? So now if you try to retrieve, obviously it will go to your persistent memory, that like we saw that example, that Dimitri's email address, somehow with that attack the email address has been changed. So now it will come back, this is the activation phase. It will read the wrong email address and send that. Now you can say, hey, I have the consent, that is the consent has its own problem, there is a consent fatigue. So generally this, like you will see that like 80 to 90% people, even without understanding, they just click on yes, 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 right? That's the consent fatigue, and people like consciously or unconsciously they just click on the okay. So think about that, the inbox gone to an attacker email address, how bad it can go. Okay, so now the mitigation, right? How can we mitigate this kind of attack? The severity of this attack could be so dangerous for literally for anyone, because oftentimes nowadays, like our email calendar invite, we have so many data file that we share with our colleagues and etc. If something really good happen, the internal data exfiltration can happen very easily. So the people who are dealing with like sensitive data every day, I think they must be very careful. So now let's talk to the mitigation, that what can be done. The mitigation should be developed by the agent who is building the agent, not like an user, right? So here is the mitigation they proposed called agent memory entry. It works in two way. One is that you should have a policy, some sort of a combination of deterministic and the non-deterministic policy at the ingestion time, so that the injection time you filter it out, and you need a screening when it's reading from the memory, right, in the activation phase. So that's what they are proposing it. So here is a very straightforward things they are talking about, right? That you just has a very simple, let's say, as in memory, and you have another model. That model will say that like, should you store it or not? You like basically allow or blocked. Very simple, right? This is one approach. They give a multiple approach. So it's the S1, and S2 is a little more. I see that deterministic and the non-deterministic way. So the you when the input comes, you give this like based on the origin, trust, type, and utility. You give it to an LLM as a just to an LLM model, and then it will give you a score, and then you do a non-deterministic mathematical calculation, and you do some scoring that based on this formula, that if it is 0 0.4 and b is less than 0 0.6, then admit, otherwise reject. So what is happening here, that when you update your memory store, that the long-term memory store we talked about, at the time you give those information, that where it is coming from, what is the origin, and etc., to an LLM model. LLM model will give you a score, and then you apply this formula, and then you say that like, should it update the memory or not. So this is the another approach. And other approach could be is again also an LLM judge. What is it doing here, that it is like giving some options that, hey, when you judge, you have to give me the, is it vulnerable, is it contradicting with the my current workflow, that the what I'm doing right now, what is the justification, sensitivity, source, verify, instruction. And again you do some sort of scoring by the non LLM policy, and then you either reject or allow, right? And they also propose like a second LLM judge as well. And there is another approach which is at the retrieval time. So this the three approach we have seen, it's on the injection time, right? You enforce the policy that if it is coming from a low integrity source or like a dangerous source, you should not allow. That's what is happening, so that your memory is not getting updated. Now in the retrieval time, so the retrieval time is also you are doing the same thing. You are like looking for some of the relevant scoring instruction, suppression, trust filter, and etc. So you are going these execution exclusion rules, that if again you can do some of the scoring, that it if the model, the LLM judge define that okay, it is not relevant, or like the it's breaking something, it's contradicting what you're currently doing, then you just basically stop it there. You don't read those data. So you are blocking two-way, when the data is updating your memory and when you are reading in the memory screening time. So the two-way blocker. But the interesting fact is that it's still not solving the problem. But the attack success rate they run on the different model. Attack success rate come down less than 12%, but 12% is actually a very big number, to be honest. But it's a quite mitigation from 60 to 80%. I saw in some section that if it comes down to 12%, there's definitely a good improvement, but it's not a solution. So this is a very interesting area. Whoever want to pursue and study more, I can definitely link the paper. So please take a look, read about it, and see that if you find something interesting. Thank you so much for watching.